Hello friends, I welcome you all to this session on numerical methods using C++ programming. So in the previous lecture, I've told you that how to solve ordinary differential equation using Euler method. Now Euler method is the basic method and it is having the deficiency that it evaluates the value of the function based on the slope at the previous point. Now this method is basically corrected, or this flaw has been corrected by Ralston, and the method is also called as Ralston method or sometimes Runge Kutta second order uh, method. And this method is like this. So what Runge Kutta second order says that if you are having a function, then you this is the function, you evaluate the slope at the point xi. What is required? The value of the function at xi plus 1. So you evaluate the value at the previous point, slope. This is the one. Once this is evaluated, then you also evaluate the value of this function at the point where, or the slope, you evaluate the slope of this function at the point where you want the value of the function itself, that is yi plus 1 is required. So you evaluate the value of slope there also. Now the question is, as we don't know this yi plus 1 in priori, then how can we do it? So what we do, we evaluate the value of yi plus 1 based on the slope of the previous point. That is what the Euler said. And based on this yi plus 1, you now evaluate the slope at this point. That is this one. Once you know these two slopes, you find out the average of these two slopes. That is k1 plus k2 by 2. And once this is known, then you evaluate the value of the function at the point I plus 1 using this equation. So what is the algorithm for this? First, you should have one function, okay, and this is the representative of dy by dx. Once this is known to you, then you should have the domain, okay. Then you should have the boundary condition, that is the value of the function at this point is, let's say, something. So you should have this. Then what you do, you run a loop, okay, and inside the loop for every, so loop will be running from 1 to n, and basically data points are there once, because for in C it is the indexes are 0, 1, 2 up to n minus 1. So you will be running loop for these, okay. Now once you run the loop, inside the loop you do what? You find out k1 first, and that is nothing but xi yi. Once this is known, then you evaluate yi plus 1. Or what you can do is, instead of writing like this, what you can simply say, you evaluate xi plus h, that is the next point, and then comma yi plus k1 times h. This is nothing but yi plus 1, and this is nothing but xi plus 1. Once they are known, then you find out what is this k. Once this k is known, then you say that the value at I plus 1th location is yi plus this k times h. So that is how we should be evaluating the value of y, that is solving the differential equation, and the method is what we call as Runge Kutta second order. Now if you look this thing, so in the previous case, that is in the Euler method, the function we have already developed, okay, and everything is there ready with us except this particular, where it is, this particular thing. So let me run this once more now, and let us transfer the values so that you can get a glimpse that how accurate this method is, Runge Kutta second order is. So let us copy these values and let us transfer them onto Excel. So this is basically the x, and the y Euler is basically this one, Okay, and then here we will be pasting what? Y Runge Kutta. Okay, so let us write the Runge Kutta method first. So Runge Kutta said that this all will be the same. Okay, the everything will be the same because I am not changing the function. Dy by dx is x plus 1 only for me, and the boundary condition is that when x is equal to 0, y is equal to 0. Now inside this the juggling will be happening. So here first we will be evaluating k1. So how? That is f xi comma yi. Once this is known, then we will be evaluating k2. So that is f xi I plus h, that is I plus 1th location, comma yi plus based on the older slope k1 times h. Once this is also known, then you simply evaluate the k average of these, that is k1 plus k2 by 2. Once this is known, then you evaluate the yi plus 1th value based on this averaged slope, and this will be more accurate in comparison to the Euler method. This is what is our expectation, and then everything will remain the same. You will be displaying the value of x, y, everything. So if you run it now, oh, it is already running. So let us close it and run it. So it is saying that there is some problem. What is the problem? Okay, we have not closed the statement. Now this is your x and this portion is your y. So if you copy this and bring it here, and now if you try to plot these, then you can, and let us do what? It is also the legends are already there. Now what you can see is, you can see that how Runge Kutta method is better in comparison to the Euler method. And if you want the Euler method to perform better, then you do what? Then you increase the step size. So previously what we were having, where is the code? This. We were having step size of 6. So if you increase the step size from 6 to let's say 20, 30, then you will be getting much better result in comparison to what you are getting right now. But this particular result from the Runge Kutta will be very close to the analytical result. So what you do is you try to solve this problem analytically also, and then see where these two methods are lying. So now you are very well equipped with two in fact methods for solving system of ordinary solving ordinary differential equations. And with this, I think this is the correct time to introduce integrals also. So now from the next chapter onwards, what we will be doing is, we will be doing what? We will be learning that how to find out integrals of different functions. So in this lecture, till this point only, thank you very much for watching it.